So let's look at the Schrödinger equation, the time-independent Schrödinger equation, which is given by, of course, p squared by 2m plus the potential energy term acting on psi of x equal to the energy eigenvalue psi of x. Okay. So now what we want to do is we want to express this in spherical polar coordinates. If you do this, then we find that the p. If I now use this expression of p, and I'm going to use this expression, of p. So p becomes h squared minus h squared 2m, a second derivative with respect to r of psi, and then we have 2h squared by 2mr d by dr of psi, and then plus v of r psi. And then we have plus 1 over 2m r squared L squared psi equal to E of psi, okay? So I have just taken the L squared away from the rest of the terms. Now, we can do some simplifications, see that these two factors of 2. Another thing we can see is that, if we were to multiply everything, say by r squared, what would we get? We would get that this term is actually independent of r. Okay? So now because we know that our Hamiltonian commutes with L squared because it's rotationally symmetric, and L squared is if H commutes with all the L's, then it must commute with L squared. And because H commutes with the Z component of the orbital angular momentum, we can expect to find simultaneous eigenbasis for H L squared LZ. Okay, that means the energy eigenstates will also be eigenstates of L squared and LZ operator. Okay, so all the machinery of the angular momentum that we have developed so far, all the insight, all the the number of eigenstates, the possible value of eigenvalues, all of that can be brought over. Okay, is this clear?
Yes, sir.
Okay, so we can then do that simplification, and then our Schrödinger equation becomes h squared r squared. So what we're doing is we're multiplying by r squared and other factors. So this is minus 2h squared r. Let me know if I make any mistakes. I'm there's no guarantee that I won't make mistakes. So the energy eigenvalue is constant, but V of R is not. So this is the R dependent operator, and it'll act on psi, and that's equal to L squared psi. Okay. So we see that the operator on the left, this guy, only depends on R, and the operator on the right, this guy, only depends on theta and phi. So this means that the differential equation we are working with is amenable to separation of variables, right?
So will the E be in front or the VR I mean, I don't know. Like 2mr square VR minus E. Wouldn't that be the?
So you mean this thing?
Yeah. I mean, I think
Yeah,
the
let's
order
see.
should be reversed.
Let's see. What you have here is a minus sign, okay? So I have
Yeah.
actually, if you see it, and the potential energy will have a plus sign relative to that. So here what we have done is that we have, that minus sign is gone. So I've actually multiplied the whole thing by a minus sign. Let's see if this works. Okay. So L squared has a minus
No, I
sign
get
here,
you.
yeah. Okay. So I think it's correct, but let's see if it's correct. I think you're right that one of the, sorry, not here. I think you're right. Yeah. H squared R. Yeah, this should be a plus sign. This should be a plus sign. Yeah. Right? Let's see. Yeah, this should be a plus sign. Thank you. Yeah. Okay, so because the left-hand side, the operator on the left-hand side is just a function of R. It only depends on R and derivative with respect to R. Whereas the operator on the right-hand side is derivative with respect to theta and phi and only depends on theta and phi. Well, it doesn't even depend on phi, only theta, like this thing. So we can assume that it'll be amenable to separation of variable. So we can write an ansatz. So our ansatz. Do you know what ansatz mean?
Test solution.
Exactly. Yeah. So we can write an ansatz to be a radial wave function, which is R, function of R, and then an angular part, which is y theta phi. Now, if I plug this in, what's going to happen is that the left-hand side, it'll only act on this. The right-hand side, this will only act on this. So we can divide both sides by this thing, and then essentially we are doing cross multiplication. And what we have is 1 over R of R, and then that, H squared R squared, del squared del R squared, the sign error I made, which may or may not be a sign error, but let me see, what did I do? Okay. Yeah, that should be a plus sign. Okay, and then H squared R d by dr plus 2mr squared E minus V of R acting on R of R. And on the right-hand side, we have 1 over y theta phi and L squared acting on y of theta phi. Okay? So the left-hand side, only depends on R. The right-hand side only depends on theta and phi. So the only way that these two things, which have completely different dependence, can be equal to each other if they both are equal to a constant, right? Right? In other words, this thing is a constant, but of course, what is this? This is just, if I ignore this, this is just L squared acting on this. So if this is constant, then let's say that, then that means that we are looking at the equation some constant times y theta phi. So have we seen this equation before?
Yes, it's just an eigenvalue equation.
Right, it's eigenvalue equation for L squared. Therefore, we know that it's the y, they will have quantum numbers of L and M. L is the total L squared quantum number, and M is the LZ quantum number, right? And this constant is simply going to be L times L plus 1 H bar squared. L Y L M theta phi. So this is going to be, my equation, right? We know this, right? Because we know that this is orbital angular momentum squared operator. Okay, is that clear?
Yes, sir.
So, you see, it's very beautiful. Like, because of spherical symmetry, we have, very nice separation of variable of Schrödinger's equation, and we didn't even have to specify the exact form of the potential energy because it just worked out because of spherical symmetry. Okay, so this is the Schrödinger equation. This is the angular part. Of the Schrödinger equation, okay? Now, what about the radial part? So the radial part, its analysis will depend, its detailed analysis will depend on the exact form of V of R, although we can make some general statements about it. So we will do we will analyze the radial part of the Schrödinger equation in either the end of this lecture or the previous lecture, okay?